Hello students, in this topic we are going to deal with internal energy. So we already told about the internal energy, and I told you we can study the internal energy in detail. So what is meant by internal energy? It is the sum of the molecular potential and kinetic energy. It is the sum of molecular kinetic energy and the molecular potential energy. So what is the difference between the normal kinetic energy and potential energy and molecular kinetic energy and molecular potential energy? When we usually say about kinetic energy and potential energy, it is macroscopic. That means mechanical. See example, a car is moving with a speed, it is having a kinetic energy. When a body is lifted to a height h, it is having a potential energy. So all those things are macroscopic. Now here we are dealing with microscopic things, like when you take the molecules, there is a force of attraction, small force of attraction between the molecules. As a result, they are having an orientation. The molecules are having an orientation. Due to their orientation, they will have a potential energy. Now, due to their random motion, the molecules are not in a fixed phase always, fixed place always. They can move. If I take some gas molecules in a container, the gas molecules are always in random motion within the container itself. So in this room there are air molecules. These air molecules are continuously in random motion. As a result of their motion, they have a kinetic energy. So due to their position or due to their orientation, the molecules have potential energy, and due to their motion, they have kinetic energy. That is what we call about molecular potential energy and molecular kinetic energy. And the sum of molecular potential energies and kinetic energies is called internal energy of the system. Okay. So it is defined as a sum of kinetic and potential energies of the molecules constituting the system as a whole, and is not of individual molecule. It is a macroscopic variable of the system and it is denoted by U. Why it is called macroscopic variable? It is not of individual molecule. It is taken about, see, the gas in the entire room. So we are taking a macroscopic quantity and studying the internal energy. We are not taking the energy of one single molecule. That is why we are saying macroscopic, and it is denoted by capital letter U. Now, internal energy is also a thermodynamic state variable. We already discussed what is state variable. It does not depend on how the system has reached that particular stage. It depends only on the initial and the final stage. It does not depend on how the system has reached that particular stage. Now, it is an extensive variable as it depends on the size of the system. It can be specified by the values of pressure, volume and temperature at that particular time. Okay, it can be specified by the values of pressure, volume and temperature at that particular time. So, internal energy, how can we measure the internal energy directly? We can't do it. You measure the temperature, and when the gas is getting heated up, you can say that the temperature increase. You can measure that with thermometer, and when the temperature increase, we will say internal energy also increases. So internal energy is the measure of temperature. Okay, internal energy is the measure of temperature, or we will say more precisely we can say like this: temperature is the measure of internal energy. So in order to see how much is the internal energy, we have to measure the temperature. That is why we say temperature is the measure of internal energy. Now, internal energy of an ideal gas is purely kinetic. I already told you internal energy means the sum of molecular potential energy and molecular kinetic energy, the first statement, sum of molecular potential energy and molecular kinetic energy. Now what I am saying is internal energy of the ideal gas is purely kinetic, because for an ideal gas there is no fixed position for the molecules, or there is no molecular attraction. So the molecules are all free to move. So since there is no molecular attraction, we can say that there is no molecular potential energy. So there is only random motion of molecule. As a result, they will have only molecular kinetic energy. That is why we say for an ideal gas, the internal energy is purely kinetic. Okay. Now see, two different modes to change the internal energy. Two different modes to change the internal energy are heat and work. So we can change the internal energy either by applying the heat or by doing some work. So let us see both the case. First, I am going to apply the heat and try to change the internal energy. So I have given an example like this. There is a balloon which is connected, which is tied to a bottle, and I am just heating it. When I heat the balloon, what will happen? When we heat the bottle, what will happen? The gas inside this gets heated up. Gas inside the bottle gets heated up. As a result, what will happen? The gas will expand and it will put a pressure on the balloon. So the gas will rise up and it will inflate the balloon. That is what you are seeing in the second figure. So when we heat the bottle, due to the difference in the temperature, heat flow take place. As a result, the balloon blows up. So due to the transfer of heat, the kinetic energy and potential energy are getting transferred from the bottle to the balloon. The molecular kinetic energy and molecular potential energy are getting transferred from the bottle to the balloon, and that is why the balloon is inflating. So here this results in the change in internal energy. Okay, so to create the change, I first gave the heat. That is the first technique. Now second technique is work. Let us see. We can do some work on the system. And as a result, the internal energy of the system changes. For example, in this example, here, without giving the heat, if I am pressing the bottle hard, then what will happen? I am just doing some work on the bottle. So I am pressing the bottle hard. So the entire air of the bottle will be transferred to the balloon and the balloon inflates. So there also the internal energy changes. So in the first case I applied the heat. In the second case I did not apply the heat. I just pressed the bottle without applying the heat. I just squeezed the bottle. So what happens? The air from the bottle is transferred to the balloon and the balloon gets inflated. So in that case I did the work for the change in the internal energy. Okay. Now the internal energy increases when the system absorbs the heat. You have to keep these points properly in mind. The internal energy increases when the system absorbs the heat, and some work is done on the system. So, how can you increase the internal energy? Either applying the heat or doing the work on the system. Now, internal energy can be decreased if the conditions are reversed. That means the system is getting cold, the internal energy decreases, or work is done by the system, then also internal energy decreases. So, that is what I just meant by change of conditions. Now, we have to see some sign conventions in thermodynamics. So, here I already told internal energy increases when heat is absorbed and internal energy decreases when heat is released. Similarly, internal energy is increased when work is done on the system, and internal energy decreases when work is done by the system. So, how do we use sign conventions and all? If heat is absorbed by the system, that heat is taken as positive. So, for measuring the heat, for describing the heat, we use Q, capital letter Q. So, if I am writing positive Q, that means heat is absorbed by the system. If I am writing negative Q, that means heat is released by the system. Okay. Similarly, work, which letter is used to represent work? W. Okay. If work is done by the system, then W is positive, and if work is done on the system, W is negative. Okay. Work is done by the system, W is positive, and if the work is done on the system, W is negative. And the third thing, internal energy. Internal energy is denoted by which letter? Yes, U. So, the increase in the internal energy is taken as positive and decrease in the internal energy is taken as negative. Okay. So, if anywhere you see U as positive, it means internal energy is increasing, and anywhere if you see U as negative, it means internal energy is decreasing. These are the sign conventions. So, just please make a note of that. Now, the next topic, how internal energy is different from work and heat. How internal energy is different from work and heat. Work and heat are not state variables, but internal energy is a state variable. Work and heat does not depend on the state variable, because actually the heat flows from hot body to cold body. So, there is a path, and the heat will flow only if there is a temperature difference. So, condition is there, path matters. Similarly, work, how the work is doing, whether I am doing positive work, whether I am doing negative work, whether work is done on the system or work is done by the system. So, work depends on the states, not only on the state, but also on the paths. Now, that is the difference between heat and work and with the internal energy. Heat and work are not state variable, whereas internal energy is a state variable. Now, they are the modes of energy transfer to system resulting in the change in internal energy. So, the internal energy will be changed only with the help of heat and work. Either I can supply the heat or I can do the work to change the internal energy. That is what I have told in the second statement. Okay, so please make a note of that. What is meant by cyclic process? Cyclic cyclic process in which it is a process in which the system returns to the initial phase after undergoing a series of changes. For example, water became vapor and then vapor turns back to water. That's a cyclic process. Then what is non-cyclic process? Non-cyclic process means the system does not return to the initial state. System is not returning to the initial state. That is non-cyclic process. A fuel burns and the fuel is doing some work on the engine and it is converting that into mechanical energy. Okay, so heat of that engine is converted into mechanical energy and the vehicle is moving. Now the driver is applying the brake. The vehicle stops at that time. Will that mechanical energy converts back to heat? No, that is just getting wasted. We can't use that. So heat can be converted into work and all the work cannot be converted into heat. So in that case, system cannot return back to the initial state. Heat cannot flow back to the engine and then that cannot be utilized again for moving the car. So system is not returning to the original state. So that is non-cyclic process. Okay, so that's all about this topic. Thank you.